for fun, right? Because we've already taken notes. This is so that we can see things moving alive, right? And you can see why I'm so upset. So your pure atomic orbitals, right? Pure atomic orbitals will look like your S and your P's. So those are pure atomic orbitals. That's how they are before we do anything else. So the S is always a perfect sphere. The P's are always perfect figure 8s. And then if we want to do an SP hybridization, keep your eyes on the screen. And I go, 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 go. To the blender I go, and I end up with that. You end up with 2 hybrid SPs that look like that, and 2 anhybrid p orbitals. Do you see why I'm so mad? Because I had to draw all that, and it still didn't do it. When I come in, so it looks all like that. When we put it all together, and this is 1 carbon, when you put it all together, your 1 carbon looks like that. And you can see there that you're going to be able to have 2 sigma only sp orbitals. Can you see that the sp will only form sigmas? So these guys would only form the sigma bonds. And this one will form your pi bond. I don't think so. I think that's just to give it a sense of dimension. So that will be what you have. So you have the SPs are forming the sigma bonds. Is everybody? So your SPs are forming the sigma bonds, while your P anhybrids will form the pi bond. So you will form 1 and 2 pi bonds for the SP. The molecular geometry is linear, okay, and it's called, of course, SP hybridized. If on the other hand, to the blender, we go ahead and throw 1 S and 2 P's to the blenders, you're going to end up with that. You end up with 3 sp2 hybrid orbitals that look like that. So there are 3 hybrids sp2, 1 anhybrid P. When they all come together to form 1 carbon, the carbon looks like this. And the carbon that looks like that will form 3 sigmas. The sp2s are used for sigma bonds. The anhybrid P for the pi bond. Better than class, right? Or no? You guys are not impressed either way, so I don't know why I'm suffering. Okay. I'm like, okay. There's no... Oh, that makes so much better. All 4 are equal. All 4 that are forming your sp3. So all of them are tetrahedral. And this is the last table that I like. And in the table that I like, okay, the table looks like that. I would add that to my notes. I don't know about you guys, but I think I would add that to my notes. I don't know if you're interested, but I say I would. When you see your carbon that was sp3, that I wrote tetrahedral, you might want to write 4 sp3. I know exactly the paper that I'm talking about. I will find it for you. Where I will write that.
It's a hybridization part of it.
All right. So I would put all that. When your carbon is all tetrahedral, the carbon has 4 sp3s, and they form all single bond. When the carbon is sp2, you can form 3 sp2 hybrid orbitals. The sp orbitals form sigma bonds. Sp orbitals form sigma bonds. I'm going to give you a little story momentarily. When you have a triple bond, the triple bond will form 2 sp, has 2 sp. The sps are used for sigma bonds. The p orbitals are used for pi bonds. Yeah? quit this one. I want to go to this one again for enjoyment. Again for enjoyment, just because we need it. We've done this again just to give you an idea how much better this could really be, or at least it was better for me. I don't know if you felt that it was good. The different types of bonding in alkanes. In alkanes, you would have, remember how we did the molecular orbital for hydrogen? Do you remember that? We did the molecular orbital for hydrogen. So for the alkanes, because the electron is in an sp3 hybridized, when the electrons come together, you will form a sigma bond, and that's called your bonding or your anti-bonding, right? So every time with a molecular orbital diagram, you would have the constructive overlap and the non-constructive overlap, that is the anti-bonding. Yes? And this is what we call the sigma bond. So that cross there is the sigma bond. So we see that when you have a carbon that is sp3 and it comes together with another carbon that is sp3 and they come closer, closer, closer. We did this in class. There's your sigma. Carbon sp3, carbon sp3, and when the hydrogens all come in, this is what we were doing in class, except this is so much easier. That was your 6 sigma carbon sp3 hydrogen S. Yes? Everybody okay? Okay, then we went ahead and say, well, this we're doing in lab today. The ethane molecule, we have the structural formula. So this one on the left is the structural formula. But really more than structural formula. Can everybody see that this is more than structural formula? Because I think what I did by structural formula was like straight angles up and down. So when you start having the wedges and the dashes, this is going to be called perspective drawing, like 3D, okay, like 3D. This is the ball and stick, and this is space filled. So take a look at what happens with my ethane. Oh, forget that. We don't have any more here, like we rotate? No. All right, take a look at alkenes. Alkenes, there's the pod, the anhydride P, and the anhydride P has that option. So the anhydride P's coming together parallel are the ones that form the pi bond. So that is the formation of the pi bond. Delocalization above and below that nodal plane. So everybody is like, okay, I know you've done this. So when your carbon is sp2 and another carbon is sp2 and they come together, there's a formation of one sigma bond right there between carbon sp2, carbon sp2. There are that pi bond above and below. And then there were these hydrogens that came here. That's what we were doing in the other class. Yes? Okay. And they look like that. Here's alkyne. In the case of the alkyne, your carbon is sp. So the carbon is sp for the alkynes. We come together. They come closer and closer. One sp forms a sigma bond. There. The hydrogens come in. They're also forming sigma bonds there. And then, well, we're missing things. And then you have the two pi bonds, and it looks like that. The comparison of bonding, they all look, and this you copied in class. You copied that in class, we're done with that. All right, let's see if you can do something. So everybody followed everything, right? I'm going to see what you drew. Okay? We got it? Yeah? All right. Let's see what we can write over here. So label hydrogen that is bonded to an oxygen that is bonded to a carbon, hydrogen and hydrogen. I've destroyed the rules. I've destroyed the rules of molecular geometry. That should be linear, but I didn't fit it all in. I have lone pairs and lone pairs. Okay. So you're just going to be doing as I want. Okay, may I say that? So my first arrow is going to be like this, and all I want you to do is label the hybridization of the carbon atoms. So you're putting down in your paper the hybridization of the carbon atoms. And yeah, this is not discussion, this is still lecture because I was too mad during lecture that nothing was working properly. It's a good thing it's working. So is it beneficial, the CD, or no? I need visuals. How are you? And even the first
SP3. So between this, there is.
All right, so did we write the hybridization? I'm gonna go from left to right. Finally, I found my color pink. What is the hybridization of the carbon? sp2. What are you gonna say about the oxygen then? What should be the hybridization of the oxygen? sp2 too, right? I mean, if you're going to form a pi bond, if the carbon is sp2, the oxygen has to be sp2. That's a double bond, that's that, right? So your carbon is sp2, oh, my lovely oxygen is also sp2, okay? We'll talk about that guy. This guy in the center, that carbon is going to be what? sp3, guess what? I don't care about him at all. That's why I'm putting it with a faint green here. What happened to the carbon at the end? This carbon then is going to be sp. Okay, if the carbon is sp, the nitrogen is then going to be sp2. All right? As in sp also, not the number 2. Also sp. All right? Also sp. These guys over here just said sp2. All right, so sp only. So this is what I want you to do. I want you to label all the bonds around the sp2 site. So all we want is to label all the bonds. I'll write that in English. Label by label all the bonds around the sp2 carbon using the new hybridization notation. I don't know what else to call this. Did you use this notation in Chem 1 and 2? The sigma carbon sp3? I don't think so. That's why I'm calling it, using it, the new. Test, what I do is I put just that arrow, just like I did before, for you to do. So help me out. Well, I remember them last Wednesday, not today. So wait, and it's Ashley Anero. Yep. I want to put an N on your end. I don't know why. I want to call it Añero. Okay, Jeanette Avila. And Nicole, yes. Rochelle.
still working the lone pairs? Or still low?
Maybe.
The lone pairs.
What about tiny
Hybridized pairs.
trunks? And Leon, Molly,
So it's like that.
and niece. And in addition to that, I have Jessica Troff, Laura, Supra, Kevin, Kyle, and he was in lecture. Yeah, like he was in lecture. Alright. Alright, so everybody is here that was supposed to be here. Very good. Thank you for perfect attendance. Alright, so this is what I did, right? I'm gonna say that this sigma bond here is different than this sigma bond here, and it's different than this sigma bond here. Can I do that? Can we say that?
Yeah.
Yeah? Alright, so my first sigma bond, it's going to be between a carbon sp2, hydrogen S. I'm going to have a sigma bond between a carbon sp2, oxygen sp2. Everybody so good still? Yeah? Everybody? You guys going to be my most brilliant OChem class ever? Carbon sp2, carbon sp3. So far that's good there? Yes? Everybody agree? Everybody? No question around anyone. Whoa, yes? And here I'm thinking my whole day is at this. How come I didn't call your name? You're Jason, right? Huh. Okay. I still don't see you. All right, or you. I didn't call your name. Okay, we'll figure this out. All right, so anyway, what happens with the pi bond? What happened to the pi bond? What is going to be the pi bond then? What are we going to call the pi bond? So my pi bond over here, that pi bond over there, I'm going to say that the pi bond is carbon P to oxygen, P also, oxygen P. Okay, where are the lone pairs of the oxygen located? In what orbital? I'll write good English. In what orbital would we find the lone pairs of oxygen? Where would we find the lone pairs of oxygen? In what orbital would we find the lone pairs of oxygen?
Would it be the unhybridized P?
Hybrid.
No.
So what happened with sp2 again? What was the deal with sp2? How many orbitals did we have for where sp2? You wrote notes. You said an sp2 hybrid had 3 sp2 and 1 pi. Did you write that?
Yes.
So 3 sp2 and 1 pi. If you have 3 sp2, you use 1 to form a sigma bond. The lone pairs are in hybrid sp2. Let's do this differently. I'm not liking the explanation at all. Let me look at oxygen for a minute. I did not like the explanation. Bad one. Oxygen is in group number 6. Right? Oxygen is in group number 6. That means oxygen has 6 valence electrons. Oxygen's 6 valence electrons are 2s2 to p4. It looks like this. In my 2s, I have 1 and 2. In my 2p's, I have Hund's rule. Remember Hund's? What did Hund say? Electrons go in with the same spin in orbitals of the same energy level. I'll say it again. This is Hund. When orbitals are at the same energy level, electrons go in with the same spin before you pair them up, right? Before you pair them up. That's the story. This is atomic oxygen before we do anything else. Okay, atomic oxygen before we do anything else. If I want to have an oxygen with a double bond, what do I have to do from this story? To have an oxygen that have a double bond, what do I have to remove before I throw into the blender? I have to remove one orbital before I throw the rest into the blender. Which one do you have to remove? To form a pi bond, you have to have atomic p orbital, meaning you cannot hybridize one of these. So you'll take one of them away, and you must leave one of these guys atomic like to form a pi bond. If not, you cannot form a pi bond. So you took one away, what's left? One S and two P's. Is everybody? What's left is one S and two P's. So to the blender, you threw the remaining, and it became sp2, sp2, sp2. And here you only have one. There you only have one. That's the one that you're going to form the pi bond. How many are left? How many are left? 5. 5 are left. Back again with Hun. 1, 2, 3, 4, and 5. This form your sigma bond. So this guy made the sigma bond. This guy made the pi bond. Which orbital are the lone pairs located? Your lone pairs are in hybrid sp2 orbitals. So you come back, in what orbital would we find the lone pairs of oxygen? In hybrid, well that says hybrid, sp2 orbitals. Because oxygen has a total of 6, there were a total of 6 valence electrons. So in order to form a pi bond, I need to leave at least 1 electron in a non-hybrid P. So that takes care of your 2, 4, 5, and 6 valence electrons. Yeah? Everybody seeing? Any question that you have that I can help out? Okay. So now you go back to the SP. Go ahead and label all the bonds around the SP. So see if you can label all the bonds around that SP carbon, just like you did before. There shouldn't be so many of them. So I see that I have this sigma bond here, right? There's going to be that sigma bond there. I think that one should be easy. I'm going to say that that's sigma bond. And this is kind of like, is there a commutative property of addition? Or just multiplication? Okay, well, it's been a long time that I teach math. So, you know the story that it's the same thing to do 2 plus 3 than to do 3 plus 2, and that commutative? Okay, so we'll use that same principle here, okay? So if you had written that you have a sigma bond between a carbon sp3 and carbon sp, okay, the student that went carbon sp3 to carbon sp, or the student that walks out and wants to jump off the bridge because that student wrote a sigma between carbon sp and carbon sp3, that's the same thing. Okay, so don't be, when people walk out of that test, oh my God, like everybody's about to just kill themselves. It's the same thing, it's the same thing. So it doesn't matter the order in which you write it. Okay, there is this sigma bond squeezing between here. the sigma bond, and we like to squeeze them. I think you asked that in class. I think people usually like to put the line in the middle as the sigma, above and below as pi. So that one in the center, I'm going to call it the sigma bond. And we said if the carbon was sp, hey, the nitrogen also has to be sp because you have the triple bond. Okay? We have these pi bonds above and below. There are two of them. They were made between the same atom, so you can collect like terms. So I'm going to say that I have two pi bonds, and they are between who and who?
C.
They're telling me Cp, Np, and that is absolutely correct. Okay, absolutely correct. Your nitrogen also needs to leave the orbitals unhybridized in order for you to form the pi bond. These form pi have to be like this, atomic like. They have to be like this, and they come parallel to one another. Okay. See if everybody understood everything I said. Where are those lone pairs located?
Oh, you need to see this one.
Where are these lone pairs then located?
It's just CP.
What orbit? I know it's on the paper.
It's just a
I
it
know
doesn't
it's
have
on the
S.
paper.
Oh,
It's just
it's just
Is everybody seeing that lone pairs? Okay, the lone pairs here have to be then in a hybrid sp orbital. Why? What happens with the sp? How many hybrid sp orbitals do you have? How many hybrid sp orbitals are there? 2. You have 2 hybrid sp orbitals. So if I have 2 hybrid sp orbitals, I use 1 to form that sigma bond. That other sp then is full with the lone pairs. Nitrogen looks like this. I'll explain it like this. Nitrogen is in group 5. So back again, nitrogen in group 5. Nitrogen in group 5 is going to look like this. In the 2p, in the 2s, into a disaster. In the 2s, nitrogen has 1 and 2. In the 2p's, nitrogen has 1, 2, and 3. So this is atomic nitrogen. Atomic nitrogen. If nitrogen throws all of these orbitals into the blender, all of them into the blender, what is the hybridization? All of them go to the blender. What is the hybridization? sp3. If all 4 of them go to the blender, okay, back again, all 4 went to the blender, you would have 4 identical shape and size, orbitals. Each of them is called sp3. Ariane, I see your hand up. Just give me 1 minute. And then we have a total of 5. So 1, 2, 3, 4, and then 5. So if they ask you about ammonia, they say they're asking you about ammonia, and they ask where are the lone pairs of ammonia located? In a hybrid sp3. Yeah? Yes, go ahead. I know there are 4 because there was 1 and 2 and 3 and 4 orbitals. So there's always going to be 4 orbitals, always, because we started out with 4 orbitals. So there's always a total of 4. All right, there cannot be any more for the story with the second energy level. That's all we're interested in. So there will always be a total of 4. If you used all 4 4 to form single bonds, and they're all sp3, okay? But if you want to form a nitrogen with 2 double bonds, okay, so to form a nitrogen with 2 double bonds, it's like you have to leave this guy out. That would be 1 pi bond. But wait, you have 2 pi bond. Oh, okay, you have to leave this guy out. So how many orbitals are remaining? Just 2. Those 2 get thrown into the blender. When those 2 get thrown into the blender, you have this, right? To the blender, you would have an SP and an SP into the blender. But over here on the side, you left the P and a P unhybridized. There's a total of 5 for nitrogen. You left 1 and 2 so you can form your pi bonds. Total of 5. There are 3 remaining, right? So you have 1 and 2 and 3. Guess what? Nitrogen again can only have a total of 3 bonds. Okay, your sp will form, the sp forms the sigma bond, and the p orbitals will form your pi bonds. Is that clear? You have to take them out when there's 1, but the story gets refined as we go through the year. So the story actually changes quite a bit. So for now, we're going to say 1, but that is, we'll add later.
This one has 2 electrons.
Okay, any other question? Yes?
Go back into the oxygen.
Yeah. Go to the oxygen. So the oxygen was the same story. Any questions? Anybody else has any questions? We all kind of good? Not good? I mean, I thought the lecture today was like a disaster in my mind. I didn't have all these pictures, so I need to like solidify it, otherwise I would not sleep at night. All right, the other thing that I didn't feel was strong enough, in my mind again, only because I've been doing the same thing for a while, was my functional groups. And now that this is working, right? And we're not, by the way, I don't think we're totally done with this. Is that okay? We're not totally done with this. I think this is totally new to organic chemistry. I don't even know if Dr. Arnaiz will even do it like this. But this is really a whole 1990s, 2000 way of teaching functional groups and hybridization. I love it, and it'll remain with us for the end of the year, till the end of the year. Okay. All right, so I wanted to show you a more systematic, organized way to look at functional groups. And the introduction of the functional groups, and I apologize, I even looked on Canvas, and I don't seem to have a nice functional groups, and I thought it was there. So I'll be working with Canvas this evening. Well, no, I'm playing bocce this evening. Okay, tomorrow. I'll be doing this tomorrow to make sure that there is something good about functional groups on Canvas. But you know, functional groups look something like that. You know, you will be using the molecular models this afternoon, and I think everybody knows from the molecular model kits that you'll be using this afternoon the colors. So the same thing happens over here. Our colors are going to be something like that, that your black will represent carbon. So I'm tying already the lab this afternoon. You can see that we're like customizing everything. The black will be the carbons, the white are your hydrogens, the red are the oxygen, the blues are the nitrogen. Yellow is usually sulfur, but we don't go there. Green are chlorine, so, and they have, of course, in case you didn't know, they have the table of content over here to figure it out. For us that we're a little bit more advanced than that, it will give you really the reactive sites of these guys. It will give you the carbon skeleton take a look that we're still using these carbon sigma bonds, carbon-carbon bonds. You don't have to know all of this, but this is all we have, okay? So these are all of our functional groups in a really kind of organized way that I don't know if I did, so I'm very happy with this organizational chart, okay? So for carbon-carbon pi bonds, I see some of you are getting ready to copy and some of you don't care. So I'm gonna just like tiptoe and dance and allow the people that actually want to copy time to copy. But we're gonna mention the carbon-carbon pi bonds, and carbon-carbon pi bonds, we have the alkenes and the alkynes. And I'll come back to the chart if you want, okay? So carbon-carbon, you wanna copy? Hey, I used to copy everything. Huh? Take a picture if you want. You guys say you take a picture and this would look good. Really? It already is too small. You have to zoom in. Alright, let's see what ours is. Oh, I did take a picture. Oh my, I feel like such a technological wizard. Check this out. Woo-hoo-hoo. All right, very good. Do whatever you want. All right, so we'll move back again. We'll move back again. I don't know if I want to bore you with the carbon-carbon pi bonds, but here we go. Just to have a little flavor. I like the alkenes. This is part of your chapter 2 still. They talk about cis and trans. They talk about cis and trans. I want to talk about that briefly. Again because you're doing this afternoon. Cis, when the groups are on the same side cis. They can both be to the top or they can both be to the bottom. Same side cis is the term, both to the top. You cannot rotate. You cannot take this guy and rotate to go to the other one. You actually have to break bond and reattach. Trans is when they're opposite side, like I'm going to cross the transatlantic. When I go from New York to Madrid, I'm crossing the Atlantic. Trans, across. You're going across. The term is across. In a line angle drawing, these guys look amazing. Take a look at how they look in a line angle drawing. Your trans looks like this. You'll see me drawing crazy things like so. That's trans. Across. Groups are opposite. The cis, I have the hardest of time because I cannot go fast. It doesn't look beautiful. I go crazy. I do better when it's upside down. Did you see that? I do better when I do it upside down. I can go faster because my volcano will have no top and it looks like that. And these are alkenes. And alkenes are carbon double bonded to a carbon. Now you know even so much. What do you know so much for the alkenes already? Carbon RsP2 hybridized. The pi bond is between the carbon P and the carbon P. So your YouTube starts running like that around here. Hybridization, what goes on. All right. Move you back. Over here. They look like that. See that they look like little worms upside down. Huh? The triple bond. Look at the halogens. I like the halogens. I didn't do halogens in class today because it seemed like it was going to be so easy. But the halogens look like that. They're called RX. RX are the halogens. Ooh. They look like beautiful colors. So RX are your haloalkanes. They're called haloalkanes for the RX. I want to put some notes on paper. My notes on paper are going to look like this. They're going to be called RX when HCl, or I. The new name is haloalkane. Haloalkane. So like fluoro, methane, bromo, whatever. Also called, the groups are also called alkyl halides. It's also called alkyl halides. Everybody okay? Adding to your notes? Still adding to notes, that's what we're doing. Okay. We did do this one in class today. Oops. We did do that. So the alcohol, right? We did the alcohols and the ethers. They look like that. We have the thiols that we put in class too, remember? Right next to the alcohols, we did that. We came back and we did aldehydes and ketones, and they're there for enjoyment. Right, so they're here for enjoyment. They look like that, space filled. My carboxylic acid. And then we did, ready? Don't fall off your chairs. Ah! Did we do all of these? Help me out. We did that. I don't think we call it acyl halide. I think I called it, did I call it acyl halide? I think I called it acid chloride or something. So it is there. We don't see him till like Chem 4 at the very end. He's not even really a functional group. It's only used a lot for reactivity. We did include the acid anhydrides. Remember, you did have acid anhydrides. We had the esters, I said. We had the amides, primary, secondary, tertiaries, right? Remember all that? So we did put all that together, yes? Some of you are going, I am extremely bored. We should have a quiz. See if you remember anything. All right, look how they look. They look so beautiful, all space filled and all. And the nitrogen looks like that, primary, secondary, tertiary. Looks like that. Primary, secondary, tertiary. Oh, I don't like it at all. No. Oh, there is Taxol also. All right, so we did all that. We did it all right. Did you see that? How we tested ourselves? We did it all right. In fact, we did better than they did. Did you see how we did better than they did?
The aromatics.
Taxol. No. No. But we were more specific than the book expects you to be. I hope you realize that. I don't even want them just called as the amide. I want it to be called like your secondary amide. I don't want it just to be called I wanted you to identify the aromatic. So we also wanted you to identify the aromatic. And we even wanted you to identify the alkene. So I think overall we've done great. Overall we've done great. And I hate to even say this to you. But I'm almost done with chapter 2. Okay? So what I want to do, I don't want to start a discussion now. What I want to do is when we see each other on Wednesday, we'll do the discussion there. Because I don't want to get too ahead of the material. So Wednesday, then we'll do the discussion since the CD seems to be working here. So, and then I think we should be able to finish all of the discussion on Wednesday, an hour and